Okay, we are live and we have to start with chapter 2. Before you dive into configuring and installing Docker, a broad survey is in order to explain what Docker is and what it brings to the table. It's a powerful tool technology, but not tremendously complicated one at its core. In this chapter, we'll cover the generalities of how Docker and Linux containers work and what makes them powerful, and some of the reasons you might use them. If you're reading this, you probably have your reasons to use container, but it never hurts to augment your understanding before you jump in. Don't worry, this chapter should not hold you for too long. In the next chapter, we'll dive right into getting Docker installed and running on your system. And for installing Docker, I'm going to use Eximius Labs premium subscription, persistence, and hopefully the next stream is going to cover the installation part, or I think this stream only. Process simplification. Because Docker is a piece of software, it may not be obvious that it can also have a big positive impact on company and team processes if it is adopted and implemented as well. Let's dig in and see how Docker Linux container can simplify both workflows and communication. This usually starts with the development story. Deployment story. Traditionally, the cycle of getting application to production often looks something like this. The following. Application developers request resources from operations engineer. Resources are provisioned and handed over to developers. Developers script and tool their deployment. Operations engineer and developers tweak the deployment repeatedly. Additional application dependencies are discovered by developers. Operations engineers work to install the additional requirements. Loop over steps 4 and through 6 n more times. N number of more times, 4 and 6. The deployment discover install dependent loop n times. Application is deployed. Our experience has shown that when you are following the traditional process, deploying a brand new application into production can take the better part of a week or a complex new system. That's not very productive, even though DevOps practices work to alleviate many of the barriers. It still requires a lot of effort and communication between teams of people. This process can be both technically challenging, expensive, but even worse, it can limit the kinds of innovation that development team will undertake in future. If deploying a new software is hard, time consuming, dependent on the resources from another team, then developers may just lead everything into existing application in order to avoid the suffering the new deployment penalty, or even worse, they may simply avoid solving problems that require new development efforts. Shit. I'm live. I can't open WhatsApp. Shit. I was about to break the rule. Post to deploy systems like Heroku have shown developers what the world can look like if you are in control of the application and majority of your dependencies. Talking with developers about deployment will often turn up discussions of how easy things are on Heroku and similar systems. If you are an operations engineer, you probably heard the complaints about how much slower your internal systems are compared with push button solutions like Heroku, which are built on top of Linux container technology. Heroku is a whole environment, not just a container engine. While Docker doesn't try to be everything that is included in Heroku, it provides a clean separation of responsibilities and encapsulation of dependencies, which results in similar boost in productivity. Docker also allows even more fine-grained control than Heroku by putting developers in control of everything, down to the exact files and package versions that ship alongside their application. Some of the tooling and orchestrators that have been built on top of Docker, Kubernetes, Docker Swarm mode, and Mesos, aim to replicate the simplicity of systems like Heroku. But even though these platforms wrap around Docker to provide more capable and complex environment, a simple platform that uses Docker still provides all of the core process benefits without the added complexity of the large system. As a company, Docker adopts an approach of batteries included but removable. This means that its tools come with everything most people need to get a job done while still being built from interchangeable parts that can easily be swapped in and out of the customer to support custom solutions. By using an image repository as a hand of point, Docker allows the responsibility of building the application image to be separated from deployment and operations of the container. What this means in practice is that development teams can build their application with all its dependencies, run it in development and test environments, and then just ship the exact same bundle of application and dependencies to production. Because those bundles all look the same from outside, operations engineer can build or install the standard tooling to deploy and run the application. Cycle described in figure 2 then assumes somewhat like this. Developers build the Docker image and ship it to registry. Operations engineer provide configuration details to the container and provision the resources. Developer trigger the deployment. Developer is doing the most of the work. This is possible because Docker allows all the dependency issue to be discovered during the development and test cycles. By the time application is ready for its first deployment, the work has already been done. And it usually doesn't require as many handoffs between development and operations team. In a well-defined refined pipeline, this can completely alleviate the need of anyone other than the development team to be involved in the creation and deployment of a new service. That's a lot simpler and saves a lot of time. Better yet, it leads to more robust software through testing of deployment environment before release. Broad support and adoption. Docker is well supported with majority of the large public cloud offerings some direct support for it. For example, Docker and Linux container have been used in AWS via multiple products like Elastic Container Service, Elastic Kubernetes Service, Amazon Fargate, Amazon Elastic Beanstalk. Beanstalk is Beanstalk. What is Elastic Beanstalk? I think I have not practiced Elastic Beanstalk. Linux container can also be used on Google App Engine, Google Kubernetes Engine, Red Hat OpenShift, IBM Cloud, Microsoft Azure, and many more. At DockerCon 2014, Google's Eric Brewer announced that Google would be supporting Docker as its primary internal container format. Rather than just being good PR for those companies, what it meant for the Docker community was that a lot of money began back to the stability and success of Docker platform. Further building its influence, Docker image format for Linux container have come to lingua franca among cloud providers, offering the potential for write once run anywhere cloud applications. When Docker released is libswarm development library, an engineer from Orchid demonstrated deploying a Linux container to a heterogeneous mix of cloud providers at the same time. This kind of orchestration had not been easy before because every cloud provider offered a different API and toolset for managing instances, which were usually the smallest item you could manage with an API. What was only a promise from Docker in 2014 has since become fully mainstream as the largest companies continue to invest in the platform support and tooling, with the most providers offering some form of Docker and Linux container orchestration as well as container runtime itself. Docker is well supported for nearly any kind of workload in production environments. If all your tooling is built around Docker and Linux containers, then your applications can be deployed in cloud agnostic manner, allowing for new flexibility that has not previously been possible. In 2017, Docker denoted its containerd runtime to cloud native donated its containerd runtime to Cloud Native Computing Foundation, and in 2019 it was elevated to the graduated project status. Today, the use of Linux containers in development, delivery, and production is bigger than ever. In 2022, we saw that Docker started to lose its share of server market to the newest version of Kubernetes that no longer required Docker daemon. But even these releases of Kubernetes rely heavily on the containerd runtime, which was initially developed by Docker. Docker also continues to have very strong presence in many developer and CI/CD workflows. So what about OS vendor support and adoption? Docker client runs directly on the most major operating systems. The server can run on Linux or Windows Server. The vast majority of ecosystem is built around Linux servers, but other platforms are increasingly being supported. The beaten path is and will likely continue to revolve around Linux servers running Linux containers. It is possible to run Windows containers natively without a VM on 64-bit Windows Server 2016 plus. However, 64-bit version Windows 10 Plus Professional still require Hyper-V to provide Windows Server kernel that is used for Windows containers. I don't care about Windows. It is also worth noting that Windows can run Linux containers outside a virtual machine by leveraging WSL2, Windows Subsystem for Linux version 2. To support the growing demand for Docker tooling in development environments, Docker has been released easy to use implementation for Mac OS and Windows. These appear to run natively but are still utilizing a small Linux virtual machine to provide the Docker server and Linux kernel. Docker has traditionally been developed on Ubuntu Linux distribution, but most Linux distribution and other major operating systems are now supported where possible. Red Hat, for example, has gone all in on containers, and all its platforms have first-class support for Docker. With the near ubiquity of containers in the Linux realm, we now have distributions like Red Hat's Fedora Core OS, which is built entirely for Linux container workloads. In the first years of Docker release, the set of competitors and service providers voiced concern over Docker's proprietary image format. Containers on Linux did not have standard image format, so Docker created its own according to the need of its business. Service providers and commercial vendors were particularly reluctant to build platforms that might be subject to whims of the company with overlapping interests to their own. Docker as a company faced some public challenges in that period as a result. To gain some goodwill and support wider adoption in marketplace, Docker Incorporation decided to help sponsor the Open Container Initiative in June 2015. The first full specification from that effort was released in July 2017 and was based on the large part on the version 2 of the Docker image format. It is now possible to apply for OCI certification for both container images and container runtimes. This is the primary high-level certified runtime, containerd, which is the default high-level runtime in modern version of Docker and Kubernetes. These are low-level OCI runtime that can be used by containerd to manage and create container. Run C is often used by default. low-level runtime by containerd. crun is written in C and designed to be fast and have only small memory footprints. Kata containers from Intel Hyper-V and OpenStack Foundation is a virtualized runtime that can run mix of containers and virtual machine. gvisor from Google is sandbox runtime implemented entirely in user space. Nabala containers provide another sandbox runtime designed. Flatpak should also be a container. Flatpak is a container. समझ गया. Space around deploying containers and orchestrating the entire systems of containers continue to expand. Many of these are open source and available both on premises and as cloud or software as service offerings from various providers, either in their cloud or of their continuing to pour into Linux. It is likely that Docker will continue to have an important role in modern internet. Docker is a powerful technology that often indicates both tools and processes that come with high level of complexity, as under the hood Docker is fairly complex. However, its fundamental user-facing structure is indeed simple client-server model. Several pieces are sitting behind Docker API, including the containerd and run C and crun. But the basic system interpretation is the client talking over an API to the server. Underneath this simple exterior, Docker heavily leverages the kernel mechanisms such as IP tables, virtual bridging, Linux control groups, Linux namespaces, Linux capabilities, secure computing mode, various file system drivers, and more. We'll talk about some of these in chapter 11. For now, we'll go over how the client server work and give you a brief introduction to the network layer that sits underneath the Linux container in Docker. Client server model. It is the easiest to think of Docker as consisting of two parts: client and the server daemon. See figure 2.3. Optionally, there is third component called registry, which stores Docker images and their metadata. The server does the ongoing work of building, running, managing your containers. You use the client to tell the server what to do. The Docker daemon can run on any number of servers in infrastructure, and a single client can address any number of servers. Client drives all the communication, but Docker servers can talk directly to image registries when told to do so by the client. Clients are responsible for telling server what to do, and servers focus on hosting and managing containerized application. Docker server on Linux host, Docker registry, Docker client on. Okay, so this part is essentially the CLI. Docker is a little different in structure from some other client server software. It has a Docker client and Docker server, but rather than being entirely monolithic, the server then orchestrates a few other components behind the scenes on behalf of the client, including the containerd, which is used to interact with run, C, and containerd. Docker cleanly hides any complexity behind the simple server API, though, so you can just think of it as straightforward client and server for most purposes. Each Docker host will normally have one Docker server running that can manage any number of containers. You can then use the Docker command line tool to talk to the server either from the server itself or if properly secured from the remote client. Now we can talk more about that shortly. Docker command line tool and Docker daemon can talk to each other over the other Unix sockets and network ports. Has registered 3 ports with the Internet Assigned Numbers Authority (IANA) for use of Docker daemon and client. TCP port 2375 for unencrypted traffic and port 2376 for encrypted SSL connections. Port 2377 for Docker Swarm mode. Using a different port is easily configurable for scenarios where you need different settings. The default settings for Docker installer is only use a Unix socket for communication with the local Docker daemon. This ensures that the system defaults to the most secure installation possible. This can also this is also easily configurable, but it is highly recommended that network ports are not used with Docker due to the lack of user authentication and role-based access control within the Docker daemon. Unix socket can be located in different paths on the different operating system, but in most cases it can be found here. /var run docker.sock. If you have strong preferences for a different location, you can usually specify this at the install time, or can simply change the server configuration afterward and restart the daemon. If you don't, then the defaults will probably work for you. As with the most software, the following defaults will save you a lot of trouble if you need to change them. Robust tooling. Among the many things that have led to Docker's strong adoption in its simple, powerful tooling. Since its initial release, its capabilities have been expanding ever wider, thanks to efforts of the Docker community at large. The tooling that Docker ships with supports building Docker images, basic deployment to individual Docker daemons, a distributed mode called Swarm mode, and all the functionality needed to manage a remote Docker server. Beyond the included Swarm mode, community efforts have focused on managing whole fleets or clusters of Docker server, rescheduling and orchestrating container deployments. Is hell a big chapter. Hell big chapter. Docker workflow.